Whenever I talk about deferred rendering on this YouTube channel, I usually mention that deferred rendering has a few advantages over forward rendering. One of them is that it more or less takes care of the problem of overdraw, which is when you have one object and you do all the lighting calculations and whatnot on it, and then you have another object that just immediately gets drawn over it and means that all the work that you just did has to get thrown away. And there's also overshading, which is a similar problem with like rasterizing very small triangles. Deferred rendering makes those sorts of situations more efficient because you figure out what's on screen first, you rasterize everything, and then you do all the lighting and shading and everything on the scene as a whole in a single pass. And I've also mentioned that deferred rendering makes it somewhat easier to handle scenes with ridiculously large numbers of lights in it. And I talked about the first thing in a video a little while ago. I made a video on depth prepass, which is how you can take care of at least the overdraw problem in a regular forward renderer. And today, we are going to talk about dealing with lots and lots of lights in a 3D scene. So what you see on screen in front of you, this is a 3D scene with a ridiculous number of lights in it. Using a regular forward renderer, and we're not doing anything special here, we've just got a forward renderer with 1024 point lights being sent in as a uniform and being computed on everything that we draw. We're getting about 12, 13 FPS. It's not amazing. Most people would not consider this really especially playable. This is my test project. If I switch over to a deferred renderer, just by virtue of eliminating the overdraw and overshading and rasterization problems that I mentioned earlier, we are going to be improving our frame rate from like 13 to 14-ish. We're going to be almost tripling that to like 43 to 44-ish. And we're not quite at 60 FPS here, but this is definitely an improvement. And this is using pretty much the exact same lighting code. The only difference is that we're doing it in the deferred pass. We're still sending a uniform array of 1024 point lights to the shader, and we're still computing 1024 point lights on every one of the pixels in the scene. Now, if you wanted to, if you have a truly ridiculous number of lights in your scene, you could look at this, you could say, yeah, 3 times improvement, and call it a day. You are, after all, if you clicked on this video, most likely making a GameMaker game and not like a huge open world AAA Cyberpunk 2077 game. And if it gets the job done, it gets the job done. But deferred rendering actually allows you to go quite a bit farther than that. And it offers some very interesting ways that you can basically only render light sources that are actually relevant to the pixels that are being shaded. So let me take a print screen here. And let me go and close out of this, because when I run the game with an uncapped frame rate, it makes my GPU fan go haywire, and it's starting to annoy me. And let me bounce over to Photoshop over here, and we're just going to paste that in. So we've got 1024 lights in the scene, and in this scene and in most scenes, most lights are not actually going to be affecting most of what you see. So all these point lights are arranged in a grid, and they're all fairly small. They have a radius of, I think I set it to 160. And if I were to like draw a circle around the area of influence of any given one of these lights, it's going to be like, there's this point light in the middle, and it's going to affect basically this area here. You've got this point light off on the side, and it's basically going to affect that area here. And there's like this point light over here. That was not the best circle I ever drew. There's this point light here, and it's mostly only going to affect the area here. Very few of the pixels in the scene are actually going to be affected by more than probably 2 or 3 lights at maximum. And having to compute all 1024 lights on every single, all 1600 by 900 pixels in the scene, most of those values are going to be 0. And even though we don't have the problem of, like, I don't know, doing lighting calculations on some object that's over here that just immediately gets overdrawn by that hill over there in the background, like that, we're still doing an awful lot of work that we really don't have to do. So deferred rendering allows you to tackle this problem in a couple of ways. I will say, right off the bat, that what I ended up doing when I was getting this video ready actually wasn't what I intended on doing going into it, and we'll get to that. So my first thought was, alright, so since we're in our deferred pass, we're basically just drawing a giant, like, rectangle, which is just the whole screen, you know? And if we wanted to, we could like divide this scene in half, and we could, for each half of the screen, figure out which lights are on that part of the screen, and we could only deal with them. So if we're gonna, like, let's draw the left half first. We could just draw that point light, and that point light, and that point light over there, and that point light over here, and we don't care about anything that's on this side of the screen. On average, that's going to cut down the number of lights that we have to actually deal with by half. In reality, there's a couple of lights that are like that straddle the boundary between the two halves, so they'll have to be included. And then at the same time, there are some lights that are like way off in the distance, like over in that direction off screen, that you can just ignore completely for like the whole screen. That is actually something that you can also do in forward rendering, but we're not going to talk about that today. And if you wanted to take that a step further, you could, let me hit the undo button a couple of times. You could, instead of dividing the scene in half, you could subdivide it into like quarters, or even like eighths like this, or 16ths like this. And now all of a sudden, for any given, I'll call them tiles, for any given tile on the screen, you don't really have to have that many lights being processed at one time. So if we do like this first upper right corner over here, there's this point light, that point light, this one, and just like a little tiny bit of the top of that one. And like you could draw this entire tile with only having to deal with 4 point lights. The middle of the scene, there might be a few more. There might be a few dozen point lights that are active at any given time. Maybe like 30 or 40 at most. And if you broke up the scene into tiles like this, and if you like did the deferred pass using like draw surface part to only draw like little bits and pieces of the G buffer at a single time, you could do like a sphere frustum check, and you could do like a little bit of 3D collision logic against the camera and figure out which of these lights belong in which tiles of the scene. And that should, keyword should, be a nice performance boost. So the problem with that is that the GameMaker VM is awfully slow, and while selectively like rendering each of these lights for each tile on the screen is definitely relieves some of the load on the GPU, given the execution speed of the GameMaker VM, we're not actually going to like be able to save a lot of time by doing that, because you then have to like do all these sphere frustum checks that are going to eat up some frame time. So maybe in the future, in like GameMaker new runtime or something, that'll be a bit of a more appealing option. But what I actually ended up doing is, and I will say I made this up myself. This is of my own invention. But with that said, it's actually not that complicated, and I'd be really surprised if I was the first person in history who thought of it. I'm sure that there are games out there that do this, and I just don't know what it's called, and I don't know what to type into Google when I'm doing research for these. So, since these point lights can be approximated by spheres, and since the influence of each light is additive, what if, instead of sending a big honkin' vector 3 uniform array to the shader and drawing the entire scene in one shot, what if we just drew a bunch of circles on the scene, we calculated the lighting influence of each of those circles individually, and just added them together? And this leads us to what I have dubbed the Deferred Renderer plus Light Accumulation Buffer. Again, I am sure that this is a thing that exists, I just don't know what it's called. So if we zoom out again to approximately the full scene, this is where we were looking before, more or less. So we're getting like 15, 16, 17 FPS in the forward renderer. We are going to get 44, 45 FPS in the deferred renderer. And using the deferred renderer plus the light accumulation buffer, we are getting 142 FPS. And that is about 9 to 10 times faster than what we were doing in the forward renderer. I would call that a win if you need a lot of lights. We're going to be discussing how to do this today. This is going to be a little bit on the complicated side. This video is probably going to run a little bit long. This is like my 5th time recording this, because the first couple attempts at this didn't come out really in a way that I liked. Let me close out of that again, because again the my GPU fan is going a little bit haywire, and it's starting to annoy me. So the first thing we're going to need to do is, in this test project, I've gone and like ripped out all the stuff that wasn't really relevant to what we're going to be doing. So like shadows, transparency, and deferred rendering, stuff from previous videos that isn't important here. I did go and add a little vertex buffer for an icosphere, which is just a 20-sided polygon and a icosahedron, think like a D20, sphere.vbuff in the game's included files. And I'm going to load that in OBJ Camera's create event. Let's get this drawing tablet out from off my keyboard so that I can actually like use my keyboard. We can do this by saying like var b equals buffer load sphere.vbuff. We can say sphere, let's call it vb underscore sphere is vertex create buffer from buffer. The buffer can be the one that we loaded. The vertex format can just be the one that we've defined up above. Position, normal, text, coord, color. We can say vertex freeze the sphere vertex buffer, and we can buffer delete like that. Not that this is like 9 kilobytes of memory, so it's not like it's going to be a memory leak or anything like that, but it feels like it's something that you're supposed to do when you're done with the buffer. So this is going to be, we're going to be loading a sphere into the game, and we're not going to be drawing this anywhere directly, but in the camera's post-draw event, when we do our lighting, we're going to be drawing a bunch of those on screen at once. So, to help visualize what we're going to be doing, and this isn't actually going to really be relevant to the final product, so if you're following along, you don't have to write this next part out. But in the Draw 3D World script, where we're actually drawing like the trees and the hills and the duck and whatnot, at the bottom of this, I can loop over this array of lighting information, and I can let's just copy that, shall we? So I is 0, I is less than array length lights I plus equals 3. Because this is a 1D array of vector 3s. We can say like matrix set, matrix world, matrix build, lights index I is our x, lights index I plus 1 is our y, lights index I plus 2 is our z. No rotation. I'm going to draw you with a scale of 160 because this the sphere model has a radius of 1, and each of these point lights has a radius of 160. And then we can vertex submit vb underscore sphere pr underscore triangle list and no texture. And this is going to draw just a whole bunch of spheres, which are basically going to have an origin at the location of every one of these point lights, and they're going to have a radius of the radius of the point lights, and they're going to be like from down here, from close up, you can sort of see the lighting on them, so you can tell that they're like massive like D20s that are sitting in the world. If you zoom out, since each of the spheres basically contains their own light, you're not really going to be able to see anything very interesting from above, except for like little corners where the light leaks out through the sides of the D20s. So when we in our deferred pass, we are going to basically just draw a bunch of these, and for the like area on screen that they take up, that is where we're going to be doing the calculations for exactly one point light, and we're going to add the results of those together. We're going to blend that with the diffuse color of our scene, and that is going to be what I call the light accumulation buffer. All right, let's get rid of this for loop there because it's not actually important. Again, it was just there because I wanted to like visualize what we're doing. So to actually do this, I'm kind of going to tear apart the deferred pass a little bit. Like, not entirely. The core of what we were doing originally is still going to be there, but the places where we do our lighting and that sort of thing are going to be moved around quite a bit. So I'm going to go and create another surface. Let's call it surf light. We're going to initialize that to -1 in the create event. You can use or not use the self.prefix. Doesn't matter. In the pre-draw event, where we basically check to make sure all of our surfaces exist before using them, we can go and just say surface underscore light is surface validate, window get width, window get height. This is not a built-in GameMaker function. I kind of wish it was. This is just going to check that a surface exists and that it is of the correct dimensions and format. And if it doesn't, it's going to give you a new one. If it does, it'll leave it alone. Next, I'm going to go into the post-draw event and the deferred combine shader, and I'm going to start ripping stuff apart. So, let's see. What can we leave alone? We can leave alone sampler depth and sampler normal in our deferred combine shader because we still do need the depth and normal information when we do our lights. U_light point, the lighting uniform is going to stay there, but it's not going to be like a uniform array. It's just going to be a uniform vec3. Light point count or light count can go away because I don't need that. We're just going to be looking at one light at a time. Z near, Z far, and the FOV, those can stay because we still need those to untransform points into view space. This array of transformed lighting points can go away, as can the light count, because, again, we don't need that. Shader set uniform integer, light count can go away. Shader set uniform F array for the point light can just become a shader set uniform F for the something that I'll fill in later. I'm actually going to start by not drawing any of the diffuse color information. I'm going to start by just drawing the lighting information, so I can comment that out and maybe come back to it later. And, like, draw surface combine. This is something else that I probably could have gotten rid of when I was cleaning out the project, because this was just here for the transparency pass, which is no longer here. But I do want to say surface set target surf underscore light. And we are going to draw our lighting information onto the light surface, and then, like, when we're done with that, we'll draw the light surface. And, I think that's all the stuff I want to rip out of the post-draw event for now. So going back to the shader, there's some stuff I can remove from here. So this is pretty much the same. It's not exactly the same. I cleaned it up a little bit, but it's pretty much the same of the deferred renderer shader from previous videos. Instead of just doing lighting calculations on a single point light, we're taking an array. We're looping over the array. So like I said, we're doing 1,000 passes through that loop. For every fragment on screen. Most of those are going to have exactly, like, 0 lighting influence because of their distance from the source. Bit of a downer. I'm going to get rid of the loop. Let's unindent this so that it's, like, in the same line as the rest of my code. Light point, that is not going to be an array anymore. I can get rid of the array index. Up here, I can change this from a uniform array to just a regular uniform. We can get rid of the max lights macro because that's not important to us anymore. Some other things that we can cut out. I don't actually need the diffuse color, because again, we're just looking at light information, and we only need depth and normal for that. The ambient light, I'm going to handle elsewhere. So let's get rid of the ambient light. We can initialize light underscore total to a vector3 of 0, or better yet, we can actually, instead of initializing the light total down here and then adding to it, we can just initialize the light total down here. And just say that equals instead of that plus equals, because we're only assigning to it once. And lastly, I'm going to get rid of final color, multiplying the diffuse color by the light total, because we're not going to be doing anything with the diffuse color here, as I said. And I'm just going to write light total to GL frag color. In this demo, the light is just going to be a pure white light. In reality, you're probably going to want to set the light color as a uniform, and you're probably going to want to set the light radius as a uniform. I didn't do that here because it's not important, and I was lazy. Let's move on. So, is this being draw cleared anywhere? It probably should be. Draw clear, C underscore black. So, when you set the lighting buffer, when you set the light accumulation buffer, you're going to want to clear that to C underscore black. Otherwise, it will, like, the light will accumulate over frames instead of, like, just within a single frame. What else do we need to do? So now we can actually start drawing the spheres. So I'm going to move the shader set uniform F into this for loop. And the light's position in view space, we're transforming that here by multiplying the light's position in world space by the view matrix. And we can set the value of point index 0, point index, come on, where did that period come from? Point index 1 and point index 2. we can matrix set matrix world and the world space X, Y, and Z of the lights. That doesn't make any sense. Matrix build. Yeah. This is going to be basically the same transform for each of these lights as we had when we were drawing it in like the regular draw event to be visible. So this is going to be the light's position and a radius of 160. And we are going to want to vertex submit VB underscore sphere with a PR triangle list and no texture. So if I run this now, we'll see something probably, but it's not really going to be exactly what we want. As it turns out, we are actually not seeing anything. That's cool. And let's see. That's because we're not actually setting up a couple of things that we should be. So for one, while the transforming the light's position into view space and then sending that to the shader as uniforms is fine, because we're doing our lighting calculations in view space position and normal and whatnot. We are still drawing our spheres in world space and sending them through the whole transformation pipeline, and we're going to need to set our camera matrices when we're drawing to the surface to that which we would have used in like our regular draw event, so our view matrix and our projection matrix. And we can do that by basically doing the same thing that we do elsewhere and say var cam equals camera get active. We can say camera set view map and set to that active camera. We can just use the view matrix that we use for the 3D part of the scene. We can also do the same with the projection matrix, but here the projection matrix is just like inlined instead of being saved to a variable, because previously we didn't really need to save the projection matrix to a variable. Again, you can use the self.prefix if you'd like or not. And let's see, now that we've done that, we can camera set proj mat underscore proj. We can set our projection matrix, and we can camera apply a regular camera like that. Our camera matrices like that, rather. Those will be reset when we say surface reset target, so we don't have to reset it when we're done. If you were not drawing onto another surface, you would have to reset them yourself. Let's run the game, and we should have something that looks still like a black screen. That's interesting. Oh, you know what I'm not doing? I'm not resetting the world matrix when I'm like done with everything else, which I should be, because if I don't reset the world matrix to the identity matrix when we actually draw the light surface, it's going to be like off in randomly the middle of nowhere. All right, so now if I run this, we have some spheres. Things look a little bit weird. It looks like we got some like geometry from the G buffer being projected onto the surfaces of the spheres. We can see that there's some lighting, which is definitely a step in the right direction. There's a couple of things that we'll need to do to fix that. One is that right now, these spheres are really just being drawn like on top of each other, which like when one sphere is drawn, it just completely overwrites whatever was behind it, and it doesn't add the lighting values together like we wanted them to. And that is, there is a way to fix that. We have at our disposal a fancy function called GPU set blend mode. That's blend enable. GPU set blend mode. BM underscore add is what we want to do additive blending. When we're done, in addition to resetting the world matrix, we can say set our blend mode back to BM underscore normal. And that should, alright, that looks wrong, but in a slightly different way. So I haven't dealt with like the UV coordinates in the deferred path in the deferred shader yet, but I absolutely love the the snow globe bowling ball like effect that you see with the textures being like mapped into the insides of those spheres. So right now we have Z right and Z test turned off, and that's okay. We don't really want Z right and Z test turned on, because when we draw our spheres, we want we don't want random parts of the sphere to be like clipped out. So we don't really care about depth writing or depth testing, but we are going to want the culling mode. Usually, you'll want the culling mode to be set to counterclockwise so that that'll cause like the front-facing parts of triangles to be rendered, but the back-facing parts of triangles to be just removed. In our case, we're actually going to want these spheres to be drawn inside out, and to do that, you could just, like,
Hey.
whatever the sphere vertex buffer you load from a file is, you could make the model inside out yourself, or, in my case, I'm going to go and say GPU set cull mode, and instead of saying cull underscore counterclockwise, we're going to set the culling direction to clockwise, and that's going to remove the front-facing triangles and leave the back-facing ones. And again, when we reset everything when we're done, we can set that back to no culling. And that is going to cause these spheres to be drawn inside out, which probably won't look that different from what we had before. At least we don't have, like, random bits of, like, spheres intersecting each other in funny ways. So I guess that's it's progress. What is that? Device lost. Did I run out of VRAM? Is my recording okay? Sometimes when that happens, my recording crashes, but it looks like it's okay. I'm actually using a CPU video encoder on OBS right now, instead of a GPU one, because, like, the 14 FPS demo that I started the video with had a habit of crashing the GPU encoder. Alright, that's nice. Where were we? So, the next thing I'm going to want to take care of is going to be in our, in Deferred Combine. You might have noticed that the UV coordinates that we were seeing were all kinds of messed up, and that is because when you draw surface stretched, the G buffer, the UV coordinates are just going to be the screen coordinates. So you're going to have like 0, 0 in the upper left and 1, 1 in the bottom right. But when we draw our spheres, the UV coordinates are going to be just whatever random nonsense happens to be on each vertex of each in the sphere. So that's not really good for us. Instead, we're going to have to calculate our screen position ourselves, our screen UVs ourselves. And that is going to look something like, let's say vec2 UVs equals gl underscore frag coord.xy divided by a vec2 of 1600 and 900. So gl frag coord is going to be a vector which contains the screen position in like absolute pixel units of whatever you're drawing. So in this this test project is 1600 by 900, so it's going to be 0, 0 in the top left and 1600, 900 in the bottom right. And to get that into a range of 0 to 1, which is like texture space coordinates, which we want them to, we're just going to divide that by a vector 2 of the screen size. This is another thing that probably should be a uniform so that this actually works at different resolutions, but for the sake of time, I'm not going to. And instead of using v underscore v text coord in these, I believe, 3 locations where that was being used, we're just going to use these calculated screen UVs. You know, I wonder if in a regular deferred renderer, like when you just did the draw surface stretched, if it would actually be more efficient to do this. Or if not to divide by a vector, to multiply by the reciprocal or whatever, because computer science. Because this value is already provided for you, and like then you wouldn't have to interpolate that extra varying across the quad. Anyway,
Hey.
not important. If I run the game now, we are going to see that we're not going to have that weird warped effect inside each of these circles. We are going to see that we have a nice, as I said, we're just drawing the lighting information now, so the brighter parts are going to be in full light. Obviously, that's how light works, and the darker parts are not going to have any light cast on them. If you were to make each of the lights a different color, you would have some fun multicolored Christmas lights on the screen right now. Alright, great. We're like 90% of the way there. So, the last thing I'm going to need to do to make this work is I'm going to need to multiply the color that is on this lighting buffer here by the actual diffuse color, and let's move this down to the bottom. So firstly, we can draw surface light, or actually we could do that secondly. So firstly, we can draw the diffuse part of the G buffer, doing nothing special, and that's going to give us an unlit scene. Alright, congratulations. Now we have like basically what we started with like 3 years ago. And we can draw the lighting surface on top of that, but now we're going to want to multiply the lighting color by the diffuse color, because if you remember from our like original lighting shader, we had something that looked like this. indentation. We had something that looked like this. We're going to take the diffuse color.rgb and we're going to multiply that by the light total. And we're going to have to say min between the light total and a vector 3 of 1, because if we have like lighting that accumulates to more than 100%, then it won't really look like anything. We don't have to do this min operation here, because when we write our lighting values to our light accumulation buffer, you can't go higher than 1 anyway. Surface RGBA8 unorm is gonna like clamp the value at 1 anyway. So all we have to do to finish this off is going to be to multiply the lighting value by the diffuse color. And we can do that by setting a blend mode. Unfortunately, GameMaker does not provide us a like a GPU set blend mode BM underscore multiply or something like that. I wish it did. multiply. I wish it did, and we can set that back to normal at the end. So instead, we're going to have to use one of the GPU set blend mode extended values, and that's going to be something along the lines of BM underscore. I have to look this up every time. BM underscore destination color. Alright, it's just desk color. It's not abbreviated in any way. And BM underscore inverse source alpha. Where's inverse source alpha? Inverse source alpha, that's going to be a multiplied blend mode, or at least it will be when you don't have like any funny transparent pixels that you have to account for, which we don't here. So now we have lighting being applied to our scene. There's one thing we don't have right now, and that is ambient light. You'll remember that I said that we would add in the ambient light term later, and then I haven't done that yet. And the easiest way to do that, I think, using this system, would be up here when we draw clear the light surface. Instead of saying draw clear to see black, we could draw clear to, like, I don't know, what was our ambient light color? It was like 25%, I think. So that'll be 404040. And we can just clear our light accumulation surface to our ambient color, and that will give us some amount of ambient light. If you want to clear it to, like, I don't know, blue or something, our ambient light color will be blue, and some funny blue trees and very dark grass, because that's just how it maths out, I guess. And that is it for the light accumulation. So if you wanted other light types, you could do basically this exact same thing with spotlights or cone lights. Spotlights and cone lights, probably if you wanted to be clever about it, you could draw a literal like cone instead of a sphere in this pass, and then like when you fall off the spotlight's influence around like the edges of it, you wouldn't have to like deal with the half of the sphere or whatever that isn't in view. Directional lights are a little bit more complicated. So for a directional light, you have the choice of like setting your lighting uniform and then just drawing another full screen quad and doing basically this. Or, since there's really no point in doing that when you're just doing this anyway, drawing the surface over the full screen, you could break up your deferred rendering pass into multiple stages. So you could start off by doing by drawing your lighting buffer, and then you could do another pass where you draw things like full screen lights or handle specularity. You could do specularity here if you like use multiple render targets in the lighting buffer and then added that on top of the diffuse color instead of multiplying it. So maybe that was a bad example. Or other post-processing effects like fog or toon shading or other things like that. There's no rule saying that you have to do all of your deferred stuff in a single draw call like this. So that's about it. There's probably a couple of ways that you could optimize this further if you really wanted to. Let's see, if I zoom all the way out, we're getting about 145 FPS. You could be a little bit more clever about like setting the world matrix here.
Hey.
One thing that we're still not doing is that we're still not calling out lights that are either completely off screen or behind us or beyond the far clipping plane or that kind of thing. And if you wanted to do a limited amount of like sphere camera frustum checks, you could do that, and you could possibly save a couple of these. There's probably a few ways that you could squeeze a little bit more performance out of this, but I'm going to leave it here. So, my name is Michael. I like wizards and dragons and making games. If you want the code for this, Look for the GitHub repository down in the description of the video. By all means, try to optimize this further, see if you can, see how much more you can squeeze out of this. I usually mention my computer specs when I'm talking about performance. I am still on my 3GB GTX 1060 and Intel 7700 without the K. You may or may not get more or less out of this code just as it is if you have some other kind of computer. One last thing, by the way, since we're not sending in, like, what did I call it earlier? A big honkin' uniform array of vector 3s for each of the lights. You can add as many lights, as many pointer spotlights as you want here without having to worry about, like, running out of uniform bandwidth. All it would entail to add more lights would be to have more iterations of the loop in GML, which isn't without performance cost, but since you have a limited amount of uniform or texture bandwidth in shaders, that does put an upper limit on how many lights you can have in a uniform array, regardless of performance. So that's another advantage that this system has. Anyway, I like to make videos on the weird stuff you can do in GameMaker, so if anything like this appeals to you, feel free to subscribe. I have a Patreon, so if you want to contribute to the channel, links to that can be found in all the usual places. You should all go check out Wizarducks and the Lost Hat, which is the game that I like to work on when I'm not doing YouTube stuff. Link to the Steam page can be found down below. I hope you all found this interesting, and I will see you all later. Special thanks to Zenjamin, VitroV, Squarecrow, Spy Die Games, Manta Ray, GameMaker, Edward Holt, and DJ Gibbles for supporting these videos. If you want to contribute to the channel, head on over to the Patreon page down in the video description to join the fun.